You are 3 years from the nearest human being, and your ship just went quiet. Not all at once. That would have been easier to process. A single catastrophic failure, an explosion, something with a defined moment you could point to. Instead, it happened the way deep space always works, slowly, then completely. First, the secondary navigation array. Then the long-range communication antenna degraded by a micrometeorite impact so small, the hull sensors didn't register it as a collision, just a statistical event, a number that changed in a log file. The kind of thing that gets reviewed in post-mission analysis when there is a post-mission analysis. Then the redundant power relay feeding the heating elements in the crew module, which means the temperature inside has been dropping for 11 hours and is currently at 8 degrees Celsius and will reach zero in approximately 6 more hours and will reach the temperature of deep space, negative 270 degrees, 3 degrees above absolute zero, the base temperature of the universe itself. If nothing changes, within a time frame, your instruments are no longer updating you on because the instruments require power too. You are 3 years from the nearest human being. The nearest human being does not know this is happening. The signal you sent when the antenna failed is traveling toward Earth at the speed of light and will arrive in 47 minutes, and the response will arrive 47 minutes after that. And by the time anyone reads the words you sent, everything about your situation will have already resolved itself in one direction or another. Space does not wait for replies. Deep space especially does not wait. Deep space is the specific variety of hostile that doesn't announce itself, doesn't escalate dramatically, doesn't give you a monster to fight. It simply removes, one by one, every assumption you brought with you from Earth, until what remains is the reality that you are an organism built for the surface of one specific planet, operating in an environment that was never modified for you, never considered you, and will not adjust on your behalf. From the observation window, it is stunning. This is the thing no one warns you about adequately. The thing that every astronaut who has ever looked at deep space from inside a spacecraft has struggled to explain in language that conveys both halves of it simultaneously. It is stunning. The stars at this distance from the sun, with no atmosphere to scatter their light and no earthly horizon to frame them, are present in a density and sharpness that photographs cannot capture. Every star you can see from Earth is still there, and there are orders of magnitude more of them visible now, down to magnitudes your naked eye couldn't reach from the ground. The Milky Way is not a faint smear across a dark patch of sky. It is a structure, a physical dimensional thing, a river of light with depth and texture, neighboring galaxies visible as discrete objects rather than theoretical points. It is, without exaggeration, the most beautiful view available to a human being. The astronauts on the International Space Station describe the moment of first seeing it as one that permanently recalibrates something in the brain, a shift that doesn't reverse when they return to Earth. Some of them say they spent years afterward unable to explain to people on the ground why they came back changed. The view does that, the scale does that, but something is wrong. Because the view is the same whether you are safe or dying. The stars don't rearrange themselves when the heating fails. The Milky Way doesn't dim when the communication array goes offline. Deep space is indifferent to your operational status in a way that is almost personal in its totality. It offers you its full beauty at the exact moment it is killing you, and the two things happen simultaneously without contradiction, because space does not experience contradiction. It experiences physics. And the physics of deep space is a list of hazards so comprehensive and so layered that when you look at it from the outside, the remarkable thing is not that it is dangerous. The remarkable thing is that we ever convinced ourselves it was survivable. But here's the problem. Radiation. Not the visible, dramatic kind, not the glowing green of science fiction. The invisible, cumulative, structural kind that does not hurt in the moment and does not announce itself and does not trigger any warning system your body has evolved to detect. In deep space, beyond the protective bubble of Earth's magnetosphere and beyond the partial shield provided by the sun's own magnetic field called the heliosphere, the radiation environment is unrelenting. Galactic cosmic rays, high-energy particles accelerated by supernovae and other cataclysmic events throughout the galaxy, traveling at fractions of the speed of light, pass through spacecraft walls and through you continuously, not occasionally. continuously. Every second you spend in deep space, particles are penetrating your skull and passing through your brain tissue, breaking chemical bonds, damaging DNA, producing secondary particles that damage more DNA, accumulating in the cellular machinery that keeps your nervous system organized. The long-term neurological effects of galactic cosmic ray exposure, studied in astronaut populations and confirmed in animal trials with simulated deep space radiation, include cognitive decline, memory disruption, increased risk of dementia, and structural changes to brain tissue visible on imaging. A Mars mission that roughly 7 months each way mounts would deliver a radiation dose to the crew that approaches lifetime safe exposure limits before they even land. A mission to the outer solar system would exceed them. This is not a problem with a current solution. The massive shielding required to meaningfully reduce cosmic ray exposure would make spacecraft too heavy to launch with existing technology. We know this danger exists and we do not yet know how to stop it, which means that every human being we send past low Earth orbit is accepting neurological damage as a condition of the journey. And it gets worse, because galactic cosmic rays are the chronic problem. The acute problem is solar particle events. Eruptions from the sun that fire concentrated streams of high-energy protons into space with enough intensity to deliver a lethal radiation dose in hours. On Earth, the magnetosphere deflects these. On the surface of Mars, the thin atmosphere provides marginal protection. In deep space, between planets, with nothing between you and the sun's eruption, a major solar particle event is a countdown. The Apollo astronauts were lucky, and that word is used deliberately by the scientists who have studied the mission timelines, because between Apollo 16 and Apollo 17, there was a solar particle event large enough that, had it occurred during either mission's transit or surface operations, the crew would have received a dose estimated to cause acute radiation syndrome and probable fatality. They missed it. Not because of planning, because of timing, because the sun happened to be quiet during those specific windows. The margin between the Apollo program being a story of triumph and being a story of tragedy was not engineering, it was luck. And luck is not a system's redundancy. And this is where things change. Because radiation and equipment failure and the cold are all external, they are things happening to the ship, to the hardware, to the body as a physical object. What deep space also does, and what is harder to quantify but thoroughly documented in the psychology of long-duration spaceflight, is what it does to the mind, not metaphorically, clinically. Isolation at interplanetary distances produces a specific and well-studied psychological deterioration pattern in otherwise healthy, highly trained individuals. The communication delay alone, which at Mars ranges from 3 to 22 minutes one way, and in the outer solar system stretches to hours, produces a form of social disconnection that has no terrestrial equivalent. There is no conversation possible. There is only the exchange of recorded messages, asynchronous, delayed, the voices of people on Earth arriving as artifacts from the past, rather than the real-time connection the human nervous system requires for stable psychological function. The crews of Antarctic winter over stations, studied as analogs for deep space psychology, show predictable patterns of cognitive narrowing, interpersonal friction, and what researchers call the third quarter phenomenon, a measurable dip in performance and morale that occurs approximately 3/4 of the way through any long isolated mission. In deep space, the third quarter is months of transit away from both origin and destination, with no possibility of early return, no rescue mission feasible within any time frame that matters, and communication with Earth reduced to the emotional equivalent of letters sent by slow boat. NASA psychologists study this, they work on it continuously. They have not solved it. The solution may not exist within current human biology, because the nervous system was not constructed for this kind of removal from everything it evolved alongside. But that's not even the worst part. The worst part is the unknown, not as a rhetorical category, but as a literal, scientifically acknowledged gap in our understanding of what deep space contains. In 2012, Voyager 1 crossed the heliopause and entered interstellar space, the first human-made object to do so, and immediately began measuring an environment that differed from our models in ways that took years to resolve and left some questions open. The density of plasma, the behavior of magnetic fields, the interaction between solar wind and interstellar medium, The boundary region behaved differently than our best predictions said it would. And Voyager 1 is a simple machine carrying simple instruments. What it reported was already enough to require model revisions. The universe outside our solar system's protective bubble is not a vacuum in the colloquial sense. It contains material, thin, cold, but present, and magnetic fields from the galaxy itself, and particle densities that shift in ways we do not fully map, and structures on scales we are only beginning to detect. We have sent exactly 2 objects into interstellar space. Both of them were launched in 1977. Both are still transmitting barely, their power supplies fading, their instruments returning data from a regime of space that no human being has ever entered and no human mission is currently scheduled to reach within any of our lifetimes. What lies between stars is, functionally, still unknown territory in the precise sense. Territory entered only by instruments too simple to report on most of what they encounter. And we are planning to send people out there. Not to interstellar space yet, but to Mars, to the asteroid belt, to the moons of Jupiter on timelines that serious space agencies are treating as engineering problems rather than theoretical proposals. We are building the vehicles, we are selecting the crews. We are calculating the radiation budgets and accepting the numbers and moving forward anyway. Because the alternative, staying, not going, deciding that the cost is too high, has never been something our species has proven capable of choosing when the horizon was close enough to see. Humans walked out of Africa across land bridges into unknown continents with nothing but stone tools and the biological drive to see what was on the other side of the next ridge. We crossed oceans in wooden boats with instruments that measured the stars with sticks. We launched ourselves into orbit on rockets that had a failure rate in the early years that would ground any modern aviation program permanently. We have always accepted the deal that exploration offers, which is the danger is real, the knowledge of the danger is incomplete, and you go anyway. Deep space does not care about that drive. It does not reward courage. It does not recognize bravery as a variable in its physics. It is cold and irradiated and silent and vast, in a way that the word vast fails to contain. A scale of emptiness so extreme that the distances between stars, when converted to human terms, produce numbers the human brain cannot hold as images. The nearest star to our sun is 4 light years away. At the speed of the fastest spacecraft humanity has ever launched, reaching it would take 70,000 years. The galaxy is 100,000 light years across. The observable universe is 93 billion light years in diameter, containing 2 trillion galaxies, each containing hundreds of billions of stars. Most of those stars with planets. Most of that space between all of those objects filled with nothing but the base radiation left over from the beginning of everything. A faint, cold hum of microwave light 3 degrees